So this lesson here is kind of a complement to what we've learned about in terms of exponent laws. Starting in grade 8 and through various grades, you learn that there's various relationships between when you're working with exponents. Well, since logarithms are inverses of exponential functions, it makes sense there's a number of logarithm laws, or laws of logarithms. And I want to start by getting straight into them. So in general, if we have log base c, and again, c can just be any base that's positive and not 1. If inside the logarithm we have two factors, in this case a times b, that's equivalent to having two separate logarithms where I'm adding these logarithms separately. So the log base c of ab is the same as log base c of a plus the log base c of b. Now there's a common mistake here, and I highly recommend all these common mistakes you write down. Again, this kind of connects back to the idea that when you're multiplying powers of the same base, you add the exponents. It's somewhat related to that. But this right here is incorrect. Thinking that the log base c of a times b is the same as log base c of a times log base c of b. But it's a very common mistake. I highly recommend you write it down. The quotient law is the same sort of idea. If we're dividing, if we have a quotient inside our logarithm, if we want, we can write it as the difference between two logarithms. And I should say all of these, again, work both ways. If you're subtracting two logarithms with the same base, you can write it as a single logarithm. Both these all go either way. A really common mistake is what I have written down right here, is thinking that you can just divide the two logarithms separately. And again, that is incorrect. The power law, probably the most important one actually, is if you have a logarithm where the input is all being raised to a power. Again, that b is the whole input of the logarithm, a, all of it is being raised to the power of b. That's the same as having that b as a coefficient. And quite often we kind of imagine moving the power to the coefficient. We're not really moving it, we're rewriting it. They're equivalent. And that's probably the most important of these logarithm laws. This one will come up the most, although they all come up to some extent. And again, a common mistake is this. Now, it may not be so obvious what's wrong here. I will say what you see here is wrong. It would be correct if there was brackets right here. If there was brackets, then it would be correct, because everything inside the logarithm is being raised to the power of d. But there are no brackets. And so in this case, only the b is being raised to the power of d. And so as it stands, this is incorrect. All right? So it's not like anytime you see an exponent inside a logarithm, you can write it as a coefficient. If the entire input of a logarithm is being raised to a power, it's always equivalent to that being a coefficient. And lastly, this here, which we're going to prove in a moment, is a way that we can change the base of any logarithm really quite quickly. So notice what I have on the left is log base c of a. Well, that's the same as log base b of a divided by log base b of c. So notice what I have here. I've taken a single logarithm of base c, and I've written it as a quotient between two logarithms of base b. And what is b? B can be anything, as long as they're the same thing. And in essence, this allows me to quickly change one logarithm from one base to another. And in terms of using a calculator, quite often we use log base 10. And so to have below is just a more specific example where instead of having a b, they're both log base 10. And this is why a lot of, especially older scientific calculators, don't have a button like this. Like a lot of older scientific calculators don't have a log base you choose of something. And that's because if I want to figure out log base 2 of 5, all I need is a log base 10 button, because log base 2 of 5 will be the same as the log of 5 divided by the log of 2. And these two logarithms here can be any base I want. We might as well use base 10 for using a calculator quickly, but they can be any base I want as long as they're the same. And that's kind of why a lot of, especially older scientific calculators, just have a log base 10 button instead of choose the base you want. All right, so with that said, I want to prove that last statement. I want to prove that what I just said is true. And I can prove it using things we've already learned about before. OK, so again, I want to prove that log base c of a is the same as log base b of a divided by log base b of c, where again, b can be any number we want. That makes sense for a logarithm, for the base. So it can't be a negative number. It can't be 1, but other than that, it's good. And so the first thing I want to do is take this here, log base c of a, and I want to write it, I'll say it just equals x. Here, let's say it just equals x, equals something. Well, this right now is in logarithmic form. I want to write it in exponential form. If I do, this becomes c to the power of x equals a. right? My output of the logarithm is the input of the exponential function. The input of my logarithm is the output, and the base of the logarithm is the base of my exponential function. Okay, what do I want to do next? I want to log both sides. I want to, we multiply sometimes both sides by a number. We square root both sides. I want to log both sides. And I'm just going to move this equal sign to give me a bit more space. The log of what base? Any base. I'll just pick a number. How about b? Okay, I'm just going to find the log of both sides. Why am I doing that? Because then I can take this x and use the power law and write it as a coefficient. So that left side of the equation I can write as x times the log base b of c equals the log base b of a. And so in practice, the idea of logging both sides of an equation is quite helpful, because using the power law, we can then imagine whatever, if we have a variable in the exponent, we can now imagine it as a coefficient. And in practice, we kind of end up getting the variable out of the exponent. That said, at this point, I'll keep my highlighting consistent. But if I solve for x, I will find an equivalent to log base c of a. Because right up here I said log base c of a is the same as x. Well, let's solve for x down here. Let's divide both sides by log base b of c. And notice what we have. We have x equals the log base b of a over the log base b of c, which is what we were trying to prove was correct. Because remember, up here, that x, I said, is the same as log base c of a. So now I've kind of proven, using various things we've learned about, that log base c of a must be the same as log base b of a divided by log base b of c. Where again, that b can be any number I want, which means I can change the base of any logarithm I want relatively quickly by remembering that last logarithm law we had in the previous page. All right, I want to now just do some algebraic work just using our logarithm laws, really just about getting a sense about how the things we can do with these logarithm laws. And so let's look at this question here. I want to simplify this. And I can simplify this down a lot. And so first of all, notice I have 3 different logarithms, all of base 7. That's convenient. That's good. First, let me just look at these two. I'm adding 2 logarithms with the same base. Well, we saw the very first thing, if we're adding 2 logarithms with the same base, that's equivalent to 1 logarithm where I'm multiplying the input. So this goes back to that very first logarithm law from the day. And so the log base 7 of x squared plus the log base 7 of x is the same as log base 7 of x squared times x. Or, why don't I just write x cubed? All right. Similarly, I can do more with the expression on the left. I'm just going to rewrite this minus 5 over 2 as a coefficient. Actually, I don't need those brackets. Right, multiplying the log base 7 of x by 5 divided by 2 is the same as multiplying by 5 over 2. Why am I doing that? Because right now I still can't put these together because I have this coefficient of 5/2 in front. But I don't have to have that coefficient there any longer, because I can now write that coefficient as a power. And so I have log base 7 of x cubed minus log base 7 of x to the power of 5/2. And now I'm subtracting 2 logarithms with the same base. I can put this together into a single logarithm where my input will be x cubed divided by x to the 5/2. This is using that quotient law, the second logarithm law I mentioned. And it's probably more obvious if I look at it this way maybe, but again, we can look at these in any direction. At this point, I can now use my exponent laws to simplify the input of this logarithm. This input, if you look at inside the logarithm, I have x to the power of 3 divided by x to the power of 5 over 2. That means I can rewrite this as log base 7 of x to the power of 3 minus 5/2. And what is 3 minus 5/2? You do a little bit of work with fractions, you get exactly 1/2. 3 whole minus 5/2 is 1/2. And so that's one of my possible simplified answers. Log base 7 of x to the 1/2. Great answer. That said, a power of 1/2, what does that mean? A power of 1/2 means a square root. So this is also the same as log base 7 of root x. And neither of these is better than the other. So that's why I'm writing both down. as well. This power of 1/2 right here, I can imagine as a coefficient. So this is also the same as 1/2 times the log base 7 of x. All of these things you see here are equivalent. None of them is actually better than the other. They're all the same. They're all good. So in terms of simplifying, any one of these is great. And this is going to happen all the time with logarithms because, you know, there's so many ways of rewriting them. That said, let's look at this example here. So I am subtracting two logarithms with the same base. So using that quotient law, I can think of this as one logarithm of base 5, where I have 2x minus 2 over x squared plus 2x minus 3. All right. That's not really simpler, but it's correct. However, though, I can factor. If I look inside my logarithm, I have a rational expression. So if I factor the rational expression inside my logarithmic function, I have 2 times x minus 1 in the numerator. And if I factor the denominator, I have x plus 3 and x minus 1. Now I can definitely simplify by canceling out that factor there. And so this must be equivalent to just log base 5 of 2 over x plus 3. And there's other ways I could write this. But I'll just leave it like that. Okay? When I say there's other ways I could write it, if I want, I can now write this as log base 5 of 2, take away log base 5 of x plus 3, right? Using the quotient law kind of backwards. Personally, I don't think that's actually simpler, but it is not incorrect. Usually, we consider things simpler when there's the least number of functions. Before I go on, when dealing with rational expressions, we usually talk about restrictions. The restrictions on something like this get really, really complex. So I will say, in the textbook will give restrictions, but you don't need to worry about them at this point. It just gets, there could be so many things to think about that it just gets too difficult for what I'm actually interested in. And right now, I'm interested in understanding these logarithms, and later on I'll talk more about restrictions. So we're looking at homework questions on this. Don't get hung up on the restrictions right now, okay? It can get really quite complex. I do want you to focus on just the simplification, really using these logarithm laws. All right, another logarithmic scale. And this is the last one I want to talk about, which is a measurement of the intensity of sound using decibels. And decibels are, again, a logarithmic scale. And the way it's figured out is right here, where it's 10 times the logarithm of the intensity of a sound divided by this I naught. So very, very, very similar to how an earthquake, the magnitude of an earthquake is calculated. In this case, there's a 10 in front of it. Okay, and again, you can read all this. There's a little chart here showing you examples. But again, the key is when you see a measurement of sound in decibels, it's a logarithmic scale, which means, yes, the bigger the number, the more powerful, the more intense the sound, but it's deceiving about the difference it makes because it's logarithmic. So let's get right to this question here. The sound of a vacuum cleaner is 80 decibels. A chainsaw is 110 decibels. It's clearly more. How many times more intense? It's really hard to tell just by looking at this. And so first, let's go back to what a decibel is and these particular sounds. So if I look at a vacuum, we know the decibels. It's 80. So 80 equals 10 times the log. And again, at this point, like before, I don't really care about this I over I naught. I care about the whole quotient together. So altogether, I'm just going to call everything inside there V for vacuum. And that V will represent really what that number there would tell me is how many times more intense the sound of a vacuum is compared to this I naught, which again is generally considered to be the quietest sound a human ear can hear. But again, that number won't even matter. What will matter is how it compares to the chainsaw. And so the chainsaw is 110 decibels, and so that equals 10 times the log of C. C representing the intensity of the chainsaw compared to the quietest sound a human ear can hear. So I need to compare V and C together. I know the chainsaw is more powerful. I know that C is a bigger value, but how many times bigger? Well, first, I can't do, eventually I want to put these in exponential form. But right now, I got this coefficient of 10 in front of each. That's pretty easy. Just divide both sides of each of these by 10. And so I have 8 equals the log of v, or I have 11 equals the log of c. These are in logarithmic form. Probably a lot easier if I put them in exponential form. And so in exponential form, each of these are log base 10, remember? I don't have to state that, so the one left becomes 10 to the power of 8 equals v. That's 100 million, which means the sound of a vacuum is 100 million times more intense, the power of the sound, compared to this I naught, or the quietest sound a human ear can hear. The chainsaw is 10 to the power of 11, which I believe is 100 billion. That said, how many times more intense is 10 to the power of 11 over 10 to the power of 8? Hope we realize I don't really need to go to a calculator at all, actually, in this case. I can just go 10 to the 11 divided by 10 to the 8, which is the same as 10 to the 3, using my exponent laws, which is exactly 1,000. So the chainsaw is 1,000 times more intense, the sound, the power of the sound. At this point, we shouldn't be surprised that, going from 80 to 110, actually in this case means a big difference in terms of how much more powerful it is. This happens with all logarithmic scales. And these are the 3 basic ones. Keep in mind, anytime if I am ever going to ask you a question, or the textbooks ask you a question about decibels or pH or the Richter scale, they always will have to give you this sort of preamble, the lead-in about what the formula is. Please don't waste your time memorizing these things. Again, the point is understanding how to work with a logarithm, not memorizing any of these formulas. All right, so the final problem is actually the first time I can explicitly start to look at how we can use logarithms to solve an exponential equation. And an investment grows at 6.6% per year. Every year it grows by 6.6%. So knowing that, how long will it take $5,000 to be worth $15,000? Let's first set this up as an equation. So my initial amount is 5,000. If it grows by 6.6% a year, that's the same as multiplying by 1.066 every year. I don't know how many years it's going to be, so that's what we're trying to solve for t. But I know I want it to equal 15,000. All right, I actually got too much blue. Let's make this. Oh, how about a lovely pink? There we go. Okay, and I did this very, very quickly because everything I've just done goes back to chapter 7, and I explained it in more detail there. But really now, how do we solve this without graphing? Well, first let's divide both sides by 5,000. Because really what I'm asking you is to figure out how long does it take for this investment to triple? 5,000 to 15,000 is 3 times more, and that's what we see right here. 3 equals 1.066 to the power of t. Okay, so how can I solve this? Well, I want to mention 2 ways of looking at it. Now, none of which involve using graphing device. One is to write this in logarithmic form. Okay, in the end, it's all the same thing, but this right now is in logarithmic form. So let's write in exponential form. In exponential form, this would be take that back. What I gave you is in exponential form. Let's write it in logarithmic form. So used to saying it the other way around. So in logarithmic form, it's the log base 1.066 of 3 equals t. Again, the input of the exponential form is the output of my logarithmic form. And what you see right here, log base 1.066 of 3, can be figured out on a lot of calculators directly, but not all of them. So let's say you have an older calculator that doesn't have a log button that you can choose the base yourself. Then I can just change this like we saw earlier. This is the same as log of 3 divided by the log of 1.066, where these can be any base I want. Might as well make it 10, because that's on any scientific calculator. But again, I can change this expression here into the expression below, and that was basically the thing that I proved about 5-10 minutes ago. That's it. The second step I did is only necessary if your calculator doesn't have a button like this. And a lot of calculators still don't, because you don't need it. All you need is to remember how to go to this. And type in log 3 divided by log of 1.066, you get about 17.2. So it takes about 17.2 years for this investment to triple. And that was by taking my exponential equation and then putting it in logarithmic form. Another way of looking at it is, it's going to be the same thing in the end, but is to take my exponential equation and logging both sides. So let me write this out again. 3 equals 1.066 to the power of t. Another way of getting to that same answer, it's about the same amount of work, is instead of writing it in logarithmic form, is to log both sides. So log. What base? Any base, as long as it's the same thing. I'll go with base 10 because, again, I'm boring and it's on my calculator. And so what's the point of this? Well, if I write this now as the log of 3 equals the log of 1.066 to the power of t, that t I can now write using the power law as an exponent, as a coefficient right there. And so I get the log of 3 equals t times the log of 1.066. And now to solve for t, all I got to do is divide both sides by, in this case, the log of 1.066, which, not surprisingly, is the exact same thing I have right there. So there's really no point in me continuing this, because at this point I can see that t is going to equal the log of 3 divided by the log of 1.066, which is exactly what I had there. It's all the same thing in the end. Really, it's a matter of opinion if it seems easier to take an exponential equation and put it in logarithmic form, or if it seems easier to log both sides. It's all the same thing. And so now, really, you can see how we can use logarithms to relatively quickly solve exponential equations. Everything we did with graphing devices in Chapter 7, we can now do using logarithms. And usually it's quite quick. Not always, but usually it's quite quick. And that's where I'm going to stop.